Section: Introduction. In this section, we explore how large language models, LLMs, and large multimodal models, LMMs, can benefit from in-context learning, ICL, by including demonstrating examples before a test query. This helps the models learn from a few shots without needing to update model parameters, leading to improved performance on new tasks without additional training. Recent studies have shown that few-shot multimodal ICL can enhance LMM performance on tasks outside their usual domain. While few-shot ICL has shown promise for both LLMs and LMMs, the impact of increasing the number of demonstrating examples on performance has been limited due to small model context windows, especially for LMMs using many visual tokens for images. However, with advancements allowing for longer context windows in models like GPT-4o and Gemini 1.5 Pro, we can now explore the effects of significantly increasing the number of demonstrating examples. To investigate how well state-of-the-art multimodal foundation models can handle many-shot ICL, we conducted a series of experiments testing model performance on 10 datasets covering various domains and image classification tasks after scaling up the number of demonstrating examples by orders of magnitude. Our key findings include: providing multimodal foundation models with many demonstrating examples significantly boosts performance compared to just a few examples. Gemini 1.5 Pro's performance tends to improve in a log-linear manner as the number of demonstrating examples increases, while GPT-4o shows less consistent improvements. Gemini 1.5 Pro demonstrates higher data efficiency under ICL compared to GPT-4o on most datasets. Batch processing multiple queries together can achieve similar or better performance than individual queries in a many-shot scenario, with lower latency and cost per example. Batch processing questions can also lead to notable performance enhancements in a zero-shot scenario, attributed to domain and class calibration, as well as self-generated examples during decoding. We also discuss related work on scaling ICL and multimodal ICL, highlighting the benefits of batch querying for more efficient and cost-effective inference. Our experiments focus on testing the impact of increasing demonstrating examples on the performance of GPT-4o and Gemini 1.5 Pro across various datasets and tasks, including ablation studies to understand the effects of batching queries. Section Summary. In this section, we explore the impact of increasing the number of demonstrating examples on the performance of state-of-the-art multimodal foundation models, GPT-4o and Gemini 1.5 Pro. By conducting experiments on 10 datasets covering various vision domains and image classification tasks, we demonstrate that providing these models with many demonstrating examples significantly enhances their performance. Additionally, we investigate the efficiency of these models under in-context learning as the number of demonstrating examples increases, highlighting the potential benefits of batching multiple queries for improved performance and cost efficiency. Section: Models. In this section, we utilized 3 advanced multimodal foundation models, namely GPT-4o, GPT-4v, Turbo, and Gemini 1.5 Pro, all of which have public API access. Since GPT-4o outperforms GPT-4v, Turbo significantly, we mainly focus on the results of GPT-4o and Gemini 1.5 Pro in the main text, while including GPT-4v, Turbo results in the appendix. We did not use Claude 3 Opus in our experiments due to its limitation of accepting only up to 20 images in one request at the time of our study. Each model has a specific endpoint for API access. For instance, the endpoint for GPT-4o is GPT-4o the 13th of May 2024. For GPT-4v, Turbo is GPT-4 Turbo the 9th of April 2024. And for Gemini 1.5 Pro is Gemini 1.5 Pro Preview 0409. We employed the API service provided by OpenAI for GPT-4o and GPT-4v, Turbo, and the API service provided by Google Cloud on Vertex AI for Gemini 1.5 Pro. To ensure consistent responses, we set the temperature to 0 for all models and used a random seed for GPT-4V, Turbo and GPT-4o. In cases where models did not provide an answer, we reran the query until a response was obtained. We evaluated the model performance on 10 datasets covering various domains and tasks, such as natural imagery, medical imagery, remote sensing, and molecular imagery, including multi-class, multi-label, and fine-grained classification tasks. We focused on image classification tasks as they are more feasible with the current models compared to tasks like region captioning that require more tokens. We ensured balanced class distribution in the demo and test sets for each dataset by sampling examples accordingly. For evaluating model performance, we used standard metrics like accuracy for multi-class classification datasets and the macro-averaged F1 metric for multi-label classification on Che Expert. We also assessed the data efficiency of each model by analyzing the relationship between the number of examples and model performance, considering zero-shot performance as a reference point. Our results showed that Gemini 1.5 Pro consistently improved as the number of demonstrating examples increased across most datasets, except for drug-OOD assay. On the other hand, GPT-4o exhibited performance improvements on many datasets with many-shot in context learning, ICL, although the improvement was not uniform across all datasets. We also explored the impact of prompt selection on model performance and found that different prompts had minimal effect on the overall improvement trend with many-shot ICL. Furthermore, we compared the ICL data efficiency of Gemini 1.5 Pro and GPT-4o across datasets and observed that Gemini 1.5 Pro demonstrated higher efficiency on most datasets. Both models benefited significantly from many-shot ICL at the optimal demo set size, showing an average improvement of around 17%. Section Summary. In this section, we utilized 3 advanced multimodal foundation models, GPT-4o, GPT-4V, Turbo, and Gemini 1.5 Pro, focusing on GPT-4o and Gemini 1.5 Pro due to their superior performance. We evaluate these models on various datasets for image classification tasks, ensuring balanced class distribution and measuring performance using accuracy and F1 metrics. Gemini 1.5 Pro demonstrates consistent improvements with more demonstrating examples across most datasets, while GPT-4o shows varying performance improvements with increasing demonstrating examples, affected by context window limitations. Section: Impact of batching queries. In this section, we explore the impact of batching queries on model performance. By grouping queries together in a single prompt, we aim to reduce the cost per query and analyze how different batch sizes affect the model's performance. We conduct our experiments using Gemini 1.5 Pro due to its excellent performance and free preview access. Our main findings show that increasing the number of queries in each batch can lead to minimal performance changes or even improvements in both zero-shot and many-shot scenarios. Interestingly, using a single query at a time is not optimal for many datasets, except for Che Expert and Eurosat. The optimal batch size tends to be among the 3 largest sizes for most datasets. Surprisingly, in the zero-shot scenario, performance significantly improves with the highest batch size on 3 datasets, with consistent enhancements as the batch size increases on UC Merced and Terra Incognita. To understand why batching queries can improve zero-shot performance, we conduct additional experiments. We investigate 3 potential benefits of incremental context learning, ICL, domain calibration, class calibration, and self-ICL. Our results suggest that including more images in the domain, showing images from different classes, and incorporating self-generated labels can lead to performance improvements under a larger query batch size. Furthermore, we analyze the cost and latency implications of many-shot ICL. While many-shot ICL does not incur additional training costs, per-query inference can be expensive and slow due to long input contexts. Our quantitative analysis shows that batching queries can significantly reduce latency and costs in both zero-shot and many-shot scenarios. In conclusion, our study demonstrates that many shot ICL with multimodal foundation models can improve performance and reduce inference costs. This approach allows for quick adaptation of models to new tasks and domains without the need for extensive fine-tuning. Future research should explore how many-shot ICL compares to traditional fine-tuning and investigate potential biases and hallucinations in foundation models under this context.